Today we are going to problem 9, 23 and 26 of chapter 2. An insulated spherical conducting shell of a radius a is in a uniform electric field if the sphere is cut into two hemispheres by a plane perpendicular to the field. Find the force required to prevent the hemispheres from separating. Part A. If the shell is uncharged. The surface charge density induced is given by equation 2.15 from the textbook, and the electrostatic pressure has a relation. And by symmetry, the force only survives in z direction, and therefore the force on the right hand hemisphere is given by below. And finally, you can calculate out that F equals to Fz equals to 9/4 times pi times epsilon 0 times electric field square and times a square. Part B. If the total charge on the shell is Q, and now the charge density is different. The total charge Q is uniform spread on the shell. So here we have a new term is Q/4 pi a squared, and follow the same calculation steps. And last, we have three terms at z direction: F1, F2, and F3. And noting that F2 points in the same direction for both hemispheres, while F1 and F3 points in opposite directions. So the total force, the force required to hold the spheres together is just only F1 and F3. So that is F net equals to F1 plus F3. And for problem 23, a hollow cube has conducting walls defined by 6 planes. The four sides are at zero potential, and the two ends on the z direction hold at a constant potential V. In part A, find the potential at any point inside the cube. First, we solve the Laplace equation for this cube, and we use the boundary condition on the four sides at zero potential, and then we can roughly get the potential formula. And next, we use the boundary condition on the other two sides at z direction. The potential on the z equals to 0 is V, and the sinh term drop to 0. Only F term survives. And next, you can use the Fourier trick to calculate out the F series. And next, the potential on the z equals to A has the same potential V equals to potential on the z equal to 0, right? So we have the relation that F series equals to E series times sinh plus F series times coch, and then we have the relation between E series and F series. So and since we have calculated out the F series relation, right? So now we got the whole series of potential. And part B, we need to calculate the center of the cube. So we use x equals to y equals to z equals to a over 2. We just directly calculate out the value. And the problem wants us to keep the keep in order to attain the we need to accurate to 3 significant figures. So the potential should be counting to the phi or mm has to be 1, 1, 5 and 5, 1. We count to how many turns? 1, 2, 3, 4, 5, 6 turns. And last, the potential is close to 1 over 3 V. And part C, find the surface charge density on the surface Z equals to A. This is a easy part. We just take a partial. We just calculate partial phi partial Z, and we use the condition that Z equals to A, and the answer is coming out. Okay, for part B, keeping only the lowest non-vanishing terms, calculate the electric field components E rho and E phi, and also the surface charge density on 3 boundary surfaces. So, and obviously, the non-vanished term, the lowest non-vanished term is m equals to 1. So we just calculate, and the field equals to partial phi partial your coordinate, and is not spatial scale. Okay, and surface charge density we have calculated that several times, so there's no need to it's nothing more. Okay, and next. And in part C, consider beta equals to pi. Show that far from the half cylinder, the lowest order turns of part B give a uniform electric field normal to the plane. Okay, now we consider beta equals pi and far from the half cylinder. Hence, our rho is much larger than r. So our E rho approach to minus C1 sine phi, and our E phi approach to minus C1 cosine phi, and the total E. Now we claim the E far from away, E far, equals to minus C1, and the direction is y direction. And then sketch the charge density on and in the neighborhood of the half cylinder. So just just calculate the charge density, right? And next, for fixed electric field strength far from the plane, show that the total charge on the half cylinder is twice as large as would reside on a strip of width 2a in its absence. So we calculate the total charge on it, okay, right? So the sigma 0 is we just calculate out on last PowerPoint. Okay, I integral over the half cylinder. You can get the total charge is 2 sigma 0 times C1, and the surface charge density on the strip is calculated by E far away, and the direction is y direction, right? The E field direction. So the charge density is minus epsilon 0 times C1, and we integral over the whole strip. The length is 2,8, and so you can get that you can calculate out that the total Q on the strip is equal to sigma 0 times C1. So the result shows that total Q on charge on half cylinder is twice as large as the charge on the strip. And final, show that the extra portion is drawn from regions of the plane nearby, so that the total charge on a strip of width large compared to A is the same, whether the half cylinder is there or not. So we calculate the whole charge on the two walls and the half cylinder. And so we just use the charge density we have calculated before and integral. So we get the result is minus 2 times C1 times epsilon 0 times A times L over A plus A over L. And now we use the approach L is much larger than A, so the Q is equals to minus 2 times C1 times epsilon 0 times L, and the total charge without cylinder is, that means the charge strip over the whole length 2L. Okay, the left side has a length L and the right side has another L length, so the total length is 2L. Okay, so after calculation you can know that on the assumption that L is much larger than A, you will get the same answer whether the half cylinder is there or not. Okay.